Now, let me explain the contents of press release from Tokushima University and Kochi University of Technology, Japan. The title of this press release is a successful optical biosensing using a dual optical cone, high sensitivity and rapid detection of biomolecule with a promising prospect. Go to background. Biosensor is a sensor capable of quantitatively or selectively measuring the biomolecule by utilizing mimicking the intricate molecular recognition ability of living organisms. It finds application in various fields, including detection of infectious pathogens such as SARS-CoV-2, health monitoring such as blood glucose measurement and the detection of environmental hormones, among others. Biosensor typically consist of a sensing component for molecular recognition and a transducer component for signal conversion. Optical biosensor, in particular, perform the signal conversion using optical method and possess characteristics such as environmental robustness, high precision, and high sensitivity. In the case of a prominent optical biosensor like surface plasmon resonance or SPR sensor, the detection involves measuring a shift in the reflected light spectrum dependent on the sample concentration. This is achieved by directing the light onto a thin gold film-coated prism surface modified with a biomolecular recognition layer. The incident light generates an evanescent wave that permits a recognition layer, and any change in sample concentration result in corresponding shift in the reflected light spectrum. In traditional method, high sensitivity sensing was carried out using a light, and the readout was accomplished through an optical signal. However, because the optical spectral shift is relatively small compared to the width of optical spectrum, device resolution limits the sensing performance. In this research, to address these two issues, high sensitivity sensing was performed using a light, and high precision readout was achieved using an electric signal. To do so, the study focused on optical frequency comb as a mean to overcome these limitations. Optical frequency comb, or OFC, possess a highly discrete multispectrum characterized by numerical optical frequency mode sequence arranged at the equal interval in comb-like pattern. However, this feature can be explained by these simple equations. Here, where the new M is optical frequency of each OFC mode, FCO is a carrier envelope offset frequency, FREP is frequency spacing, and M is a mode number. Since FREP and FCO are on the order of tens of megahertz in terms of electric frequency signal, this equation implies an equality between the left hand optical frequency signal and the right hand electric frequency signal. For example, by phase locking a FREP and FCO to an electric frequency standard, by the laser control, it becomes possible to transfer the uncertainty to new M based on this equation, allowing the OFC to be utilized as optical frequency ruler guaranteed by an electric frequency standard. On the other hand, when the optical fiber sensor are placed within the fiber OFC resonator, The sample concentration dependent optical spectral shift, so nu-M shift, is converted into the electric signal of FREP based on this equation. In other words, the OFC function as a frequency converter from optical to electric regions. As a result, the electric frequency readout optical biosensing become feasible. By converting to an electric frequency signal, not only can high precision measurement be achieved based on the electric frequency standard, but also advantages such as the speed and simplicity can be imparted. In this context, we refer to this technique as a biosensing OFC. One remaining challenge in optical biosensor is the temperature drift of sensor signal. Due to the high sensitivity of biosensing OFC, the sensor signal of FREP is affected not only by change in sample concentration, but also by variation in ambient temperature. For instance, the graph on the right illustrates the time-dependent change in sensor signal under the condition of constant sample concentrations. It shows a uniform shift in FREP1 of sensor signal in response to the change in the resonator's ambient temperature, indicated the temperature drift. To mitigate this temperature drift, active dummy temperature compensation was employed. This method is commonly used in strain gauge temperature compensation and involves preparing two strain gauge with identical properties. One of them is attached as an active strain gauge at the strain measurement location, while the other is placed at the location where the no strain is generated, serving as a dummy strain gauge. The active strain gauge measures both the strain and the temperature change, while the dummy strain gauge measures only the temperature change. Assuming that the temperature behavior is same for the both strain gauge, taking the difference signal between the active and the dummy strain gauge allow for the measurement of strain only, even in the presence of temperature fluctuations. This concept was applied to the biosensing OFC. Identical biosensing OFCs were prepared in dual-com configuration. One of them served as the active sensing OFC, measuring the both sample concentration change and the temperature drift or temperature change, while the other function as dummy sensing OFC measuring the temperature change only. Assuming that the temperature effect are similar for both, taking the difference signal between the active and dummy sensing OFC, so delta FREP or FREP1 minus FREP2, enables the measurement of sample concentration only, even in the presence of temperature fluctuation. This is the experimental setup. Pair of fiber OFC resonator are prepared, and the fiber biosensors are placed within this resonator. One of the sensors is an active sensor with a biomolecular recognition layer surface modified, while the other sensor serves as a dummy sensor with no surface modification. Both are placed within the same sample cell. The electric frequency signal from the active sensing OFC and the dummy sensing OFC, so FREP1 and FREP2, are measured with a high precision relative to a revision frequency standard. As a reference, the difference frequency signal of delta FREP is then calculated. Here, an example applied to the detection of SARS-CoV-2 N protein antigen is presented. This graph shows change in sensor signal when the antigen concentration is increased in a stepwise manner. On the left, you can see the change in the FREP1 signal of active sensing OFC and FREP2 signal of dummy sensing OFC. In both cases, temperature drift is observed. However, in the FREP1 signal, there are no apparent stepwise change in response to sample concentrations. This suggests that a small sample concentration-dependent shift is buried under a significant temperature drift. To address this, the right graph shows the calculated difference frequency signal of delta FREP between FREP1 and FREP2. The temperature drift is largely suppressed, and the stepwise signal change can be observed, indicating that it is possible to measure the sample concentration change without the influence of temperature drift. Based on these measurement results, the relationship between sample concentration and the sensor signal was plotted using a red plot. Curve fitting was performed on the plot using a theoretical model function indicated by purple line, and then so detection limit was calculated. It was confirmed that the detection limit of 37 attomolar could be achieved within the measurement time of 10 minutes in this study. In summary, the optical to electric frequency conversion capability of OFC enabled the application of OFC-based biosensors. The active dummy temperature compensation using a dual OFC configuration significantly mitigates the temperature drift. In the sensing of SARS-CoV-2, a balance between high sensitivity and rapidity was achieved. Thank you for your kind attention.